Number two, a positive charge of 50 microcoulombs is placed in an electric field of 50,000 Newton per coulombs directed upward. What mass should the charge have to remain suspended in the air? Now, the first question you would like to ask yourself: how can you form an electric field? To form an electric field, you need a power source, and you also need two metal plates. One will be cathode and the one will be the anode. Anode is a positive charge metal plate, while cathode is a negative charge metal plate. So, for instance, I have a negative charge metal plate, and below it, I have a positive charge metal plate. By the way, if you haven't watched part one of this video, kindly click on the link that just pop out at the top right hand corner in order to have access to the part one. This is the part two. In the video, I explained everything you need to know about electric field. So this is the positive charge metal plate, which is also known as anode. Then we need a power source. It can be a battery, it can be an electricity, it can be anything. So let's assume it is a battery. So this is the negative terminal of a battery, and assuming this is the positive terminal. So this negative and this positive. So the positive terminal will be connected to the positive plate, and the negative terminal will be connected to the negative plate. So whenever this takes place or occur within this region, electric field will tend to occur. Now they said a positive charge of 50 microcoulombs is placed in an electric field. So assuming we have an electric field this way, then within it, a 50 microcoulombs point charge is placed there. Now we are given the exact direction along which the electric field is moving. It is moving towards the upper part. And this makes sense because we know that for positive charge, electric field will tend to move away from them, and for negative charge, electric field will tend to move towards them. As you can see, this arrows tends to be showing the direction at which the field is leaving this positive charge and trying to enter the negative charge. That's interesting. So we are asked to find the mass of the charge that will make it suspend in the air. So let's go back to the definition of electric field. We know that E is equals to F over Q. Now we discussed in the part one of this video that F, when an object is suspended in here, it is given as mg. Now what we are going to do is to replace F with mg, and we are going to have E to be equals to mg divided by Q, as our main goal is to solve for the mass. So what I'm going to do in this case is to cross multiply. If I cross multiply, then I should have EQ to be equals to mg. And what I'm going to do next is to divide both sides by g. And dividing 2 by g, the mass of the object will be indeed equals to the value of the electric field multiplied by the quantity of the charges, or divided by the acceleration due to gravity. By the way, keep in mind, the g is a constant value that is always 10 meters per second squared, approximately. So what I'm going to do next is to substitute. The electric field is 50,000. I'm going to put that. And the quantity of charge is 50 microcoulombs. 50 microcoulombs is the same as 50 times 10 to the power negative 6 coulombs, because we need to convert it. So I'm going to write it as 5 times 10 to the power negative 5. And I'm dividing this with 10. So what I'm going to do next is to type this into my calculator and have my answer once and for all. And I have my mass to be equals to 0.25. So if you type that properly, you should have 0.25 kilogram. And this is the solution to this problem. Number 3. An electron is released from rest in a uniform electric field and accelerates to the east to a rate of 4.0 times 10 to the power of 6 meter per second squared. What is the magnitude and direction of the electric field? So let's begin by figuring out all the quantities given to us. We are given the linear acceleration. to be 4.0 times 10 to the power of 6 meter per second squared. They mention electron, and we know that the mass of an electron is about 9.1 times 10 to the power of negative 31 kilogram. However, I would like to tell you and disclose the mass of proton, likewise the charge of electron, and also the charge of proton. As in some problems, you might not be given and you'll be needing them. So they are constant value that you want to keep in mind. So this is for electron. This is for proton, though we don't need it for this problem. The mass of proton is 1.7 times 10 to the power of negative 27 kilogram. It's no more in news that one charge of an electron is simply equals to negative 1.6 times 10 to the power of negative 19 coulombs. And that of proton tend to be similar to that of electron. The difference is just that the sign is not negative. So they are something you want to keep in mind. So let's continue with our problem. So these are the two quantities that's given to us. We are asked to find the magnitude and direction of the electric field. So what formula should we use? It turns out that electric field is, according to definition, expressed as F over Q. And since the object is released from rest, the object or the charge electron tends to be moving with a linear acceleration. Therefore, we can replace F with ma according to Newton's second law. And I'm going to have ma divided by q. And lastly, I can solve for the electric field magnitude. So the mass is 9.1 times 10 to the power of negative 31, and the acceleration is 4.0 times 10 to the power of 6. And I'm going to divide that with the charge of electron. The charge of electron, I said, is indeed equals to 1.6 times 10 to the power of negative 19 coulombs. And I have it this way. So just like before, I'm going to type everything to my calculator in order not to waste much of our time. And if you type that properly, you should get 2.27 times 10 to the power of negative 5 Newton per coulombs. And this is the magnitude of the electric field. Now, some of you might have interest in knowing the visual illustration of this problem. So let me disclose that. So according to the problem, they said an electron of charge 1.6 times 10 to the power of 19 coulombs start from rest. So let's assume this is the charge. Since this is an electron, it's going to carry a negative charge. So it is directed, or it accelerates towards the east. And therefore, this is the direction of the electric field. Now, in a case whereby you are asked to find the direction of the electric force, what would you do? Good. It should be opposite to that of electric field. So if the electric field is directed towards the east, then the electric force will be directed towards the west. Simple as that. So that is easy way to identify the direction of electric force given that of electric field. Number 4. A positive 40 microcoulomb point charge is placed at the origin. Calculate the magnitude and direction of the electric field created by the point charge at the following location. Point P 5 meter, 0 meter, and point S 3 meter, 4 meter. These points are given to us in coordinate form. And in Cartesian plane, we know that coordinates are represented of the form x, y, which means the first value will be the value along the positive or negative x-axis, while the second value will be along the positive or negative y-axis. So first, let's draw a Cartesian plane. So I'm going to use a ruler to have a clear diagram. So this is the origin. And according to the problem, a 40 microcoulomb point charge is placed at that origin. So therefore, I have a positive microcoulomb point charge. Now, we are asked to calculate the magnitude and direction of the electric field created by the point charge at the following location. The first point is 5 meter, 0 meter. That is, the coordinate along the x-axis is equals to 5 and the coordinate along the y-axis is equals to 0. So assuming I move 5 units to the left, then I need not to move any unit towards the y-axis because the value along the y-axis is indeed 0. So now my main goal is to calculate the electric field magnitude, and therefore we have point P to be around there. This problem will make us to introduce another formula that can help us to calculate the magnitude of an electric field. And the formula is indeed described as this. The electric field can also be calculated of the form kq over r squared, where r is the distance between a particular point charge and the given charge, while the q is the magnitude of a charge, and k is the constant of proportionality that is about 9.0 times 10 to the power of 9. And its unit, it's simply Newton meter squared per coulomb squared. So that is what we are going to be using right now. However, if you want to know how this formula is derived, you can always use the idea of Coulomb's law to get that. But that won't be in this video. So let's move on. So in order to calculate the E right now, the magnitude of the E, what I'm going to do is to substitute. So therefore, E will be equals to the value of K we said is 9.0 times 10 to the power of 9. Then multiply by the quantity of charge is 40 microcoulombs. And since it is in microcoulombs, I'm going to multiply with 10 to the power of negative 6. And I'm going to divide that with the square of the radius, 5 squared. So right now, I'm going to type that into my calculator and have my final answer. And if you type that properly, you should have 14,400 Newton per coulombs. And this is the magnitude of the electric field. Now, what about its direction? Since the 40 microcoulombs point charge is positively charged, and according to what we discussed in part 1 of this video, we said the direction of the electric field formed by a positive charge will extend away from that charge. Therefore, it will move towards the east at point P. So the direction will be east. So the direction is east at point P, formed by the 40 microcoulombs point charge. So that is it for this problem. Number 5. An electron initially at rest is placed in an electric field of 2 times 10 to the power of 4 Newton per coulombs and is directed to the west. The distance between the plates is 1 centimeter. What is the acceleration of the electron due to the electric field? Part B. What is the speed of the electron after it leaves the hole? So let's begin. So what I'm going to do in this problem is that I would like to do the visual illustration for you in order to see the beauty behind it. Now, the main key points I will use to draw the visual illustration is that it is given in the problem that the electric field is directed towards the west. And for this to occur or take place, we need to have a positive charge plate standing vertically and a negative charge plate standing opposite to it, such that the electric field will be tending to leave the positive charge and entering the negative charge in order to be directed towards the west. And I think I get that wrong, since according to the cardinal point, this is north, south, west, east. So I think the negative will be here, while the positive will be here, such that it will now be moving this way. So that's how the diagram is going to look like. So let's draw a charge plate. So for the first charge, this is a negative charge. And for the second one, we have a positive charge. However, this positive charge will have a hole because the electron have to leave the hole according to the problem. Initially at rest, they place electron directed to the west. The distance between the plates is 1 centimeter. Okay, it need not to have a hole. You can just draw it once and for all. Perfect. Okay, think I get that diagram properly. So it the electric field is directed towards the west, so it's going to go this way. So this is the electric field and it's westward. Okay. Now an electron initially at rest is placed inside the electric field. So this is an electron and it's at rest. So we are asked to find the acceleration of the electron due to the electric field. So we want to find the acceleration of the electron due to the electric field. The electric field is given to us as 2 times 10 to the power 4 Newton per coulombs. And we are given the distance between the plates. Even though it's irrelevant, we won't use it in any case. But let's continue anyway. We might use it in part B. So the next thing we need to consider doing is to write out the mass of an electron. Earlier we said the mass of electron is 9.1 times 10 to the power negative 31 kilogram. Now we can find the acceleration of the electron using this formula. E equals ma over q. Since the quantity of charge of an electron is equals to 1.6 times 10 to the power of negative 19 coulombs. So we have everything we need to solve for A in this problem. Now, I'm just going to solve for A by just cross multiplying. Then I'm going to have E to multiply Q to be equals to MA. And I'm going to divide both sides by M. And I'm going to have A to be equals to EQ divided by M. So what I will just suggest is that you should make sure you master all those formulas that we can use to find the electric field and how they relate to one another. And make sure you master how they work so that you won't be mixing them up. So now the value of A will be equals to the electric field, which is 2 times 10 to the power 4. Then multiply by the quantity of charge, 1.6 times 10 to the power negative 19. Then divided by the mass, 9.1 times 10 to the power negative 31. So I'm going to type that into my calculator right away. So I have my final answer. So if you type that properly, you should get 3.52. That's a very large number times 10 to the power 15 meter per second squared. And this, the rate at which the electron accelerates. So part B, what is the speed of the electron after it leaves the hole? Okay, it turns out that we will need a hole at which the electron will tends to emerge out of the electric field. So therefore, we need to leave a space at this region. Let's begin. When the electron begins to move, it needs to push apart. It's going to move this way. Perfect. Now, let's calculate the speed. Well, to calculate the speed in this case, we will need to use some of the kinematics equation of motion formula. So, which of them are we to use in this case? We have the acceleration, we have the distance, and we have the initial velocity, which is 0. So, we need the final velocity at which the object is moving right now. So, let me write that out. So, we are not in need of this anymore. So, the acceleration is 3.52 times 10 to the power 15 meter per second squared. And the distance d is given as 1 centimeter. And in this case, it turns out to be 0.01 meter. By the time we divide it by 100, then we need u. U is given to us as 0 because the electron starts at rest. And we need v to be the final velocity. So which of the equation of motion should we use that relates all these four quantities together? It turns out that we can use the v squared equals u squared plus 2as. This will surely work. Now, so for v, we can just find the square root of u squared plus 2as. U is 0, so I'm going to substitute that. Then I'm going to have 0 plus 2 multiplied by 3.5 2 times 10 to the power 15, then multiply by 0.01. So just like before, I'm going to type that into my calculator and I have my final answer. And finally, I got the final speed to be equals to 8.4 times 10 to the power of 6 meter per second. And this is the final solution to this problem. Number 6. The electric field at point X is 2 meters to the right of a certain positive charge is 100 Newton per coulomb. What will be the magnitude of the new electric field if option A, the magnitude of the positive charge doubles in value? So let's write what is given to us. So we are given that there's a particular point X which is 2 meters to the right of a certain positive point charge. So let's say I have a positive point charge, and to the right of it I have a distance of 2 meters to a point X. And we are given that the charge is positively charged and the electric field of that charge is 100 Newton per coulomb. So we have to find the new magnitude of electric field when the charge doubles. So we know that E is equals to KQ over R squared. When you have to check or test how a particular quantity will change relative to another one, a simple thing you would like to do is that just check out of those quantity which of them is changing, which of them is constant. If any of them is fixed, replace them with one. Whichever change, replace with what it changed to. So I want to know the value of the electric field when the quantity of charges doubles. So it turns out that I'm going to replace K since it doesn't change with 1. I'm going to replace the quantity of charge with 2 because it doubles. Initially it is Q. By the time it doubles, it becomes 2Q. Then divided by R doesn't change. I'm still having it 1 squared. This turns out to be equal to 2, which implies that the electric field will also doubles. Another way you can see this is to check the relationship between those quantities. Since quantity of charge and the electric field tends to be directly proportional to each other, then if the quantity of charge change with any unit, then the electric field will also change with that same unit. That's another way around. The last way is to substitute. If it is an electron, or if the field, we are not actually given the magnitude of the quantity of charge anyway, so we can't really use that formula. What I wanted to say earlier is that you can substitute the value of K, the value of R, and the value of Q. But unfortunately, we are not given the value of Q. So we can't really say. Well, we can use a proton, the mass of proton, to check how the field is going to change. But I think the two previous methods are quite straightforward. So that is the answer to part A. The electric field is going to double as well. Part B, what will be the new magnitude of the electric field if the distance between the charge and the point, and point X doubles? This is the charge, this is point X. When this value doubles, it becomes 4. Okay, perfect, it becomes 4. And we know that E is equals to KQ over R squared. Now, K doesn't change, it remains 1. Times Q doesn't change, it remains 1. Now, R has changed, becomes 2, it has doubles. Okay, that's 2 squared. That's equals to 4. That's 1 over 4. So it turns out that if the distance between the charge and point X doubles, then the electric field is going to reduce by a factor of 4. Simple as that. You can see that it's going to reduce by a factor of 4. Another way using the relationship is that since the electric field is inversely related to the square of the radius, it means if the distance or radius change with any unit, then the electric field will decrease by the square of that unit. So if the distance doubles to 4, then the electric field will reduce by 1 over 4. Simple as that. And that is the answer to part B. Now, what about part C? For part C, We have to find the new electric field when the distance between the charge and the point X reduces by a factor of 3. So this is the charge, this is point X. The distance between them is 2 meters. Now we need the new electric field when the distance becomes 2/3. So very, very small of X, like it reduces by a factor of 3. So what we are going to do in this case is to begin the substitution. E equals KQ over R squared. So K is not changing, multiplied by 1. Q is not changing, multiplied by 1. Then divided by R is now 1/3 of the initial value. 1/3 of the initial value, that's 1/3. So 1/3 squared. So this becomes 1 divided by 1/9. And bringing this to the top, it becomes E equals 9. So therefore, if the magnitude of, or if the distance between the charge and point X reduces by a factor of 3, then the electric field will increase by 9. And for the last one, we should find the new magnitude of the electric field when the charge triples. When the magnitude of the charge triples and the distance is reduced by 1/4. So it means we need the charge when it triples, that's 3Q. And this is the Q, it's the Q. Then this reduced by a factor of 1/4. So that will be 2/4. And 2/4 is 1/2, 1 second. So of X. So the quantity of charge and the radius as changes. So E will now be equals to K is 1 multiplied by the value of Q, that's 3, then divided by this changes by 1/4, the radius. So that's 1/4 squared. And that will be indeed equals to 3 divided by 1/16. And that will becomes 3 multiplied by 16. And 16 times 3 is indeed equals to 48. So it means for part D, the electric field will increases by 48. And that is the solution to this problem as well. So what's just thing to keep in mind is that if you are having the electric field to be related in terms of the constant of proportionality, the quantity of charge, and the radius squared. If you have the formula to be expressed as this, then you need to know that if the quantity of charge increases, then the electric field will also increases. And if the quantity of charge decreases, then the electric field will also decreases. Why for the radius? If the radius increases, then the quantity of charge, the electric field rather, will decreases by the square of the factor along which the radius increases. While if the radius decreases, then the quantity of charge will begin to increase. If the radius decreases, the quantity of charge, the electric field rather, will increases. So those are the basic things you need to know about electric field. I think I almost forgot one question to answer. I just recalled, and that is question number 4. I didn't answer the part B. So which is this? That is the electric field created by the point 3 meter and 4 meter. So I'm going to suggest you use that as a practice problem. That you can send your solution in the comment section for me to review and give you feedback. Thanks for watching. Hopefully you find this content helpful. If you haven't subscribed, please do subscribe to my channel. See you guys in the next video. Thank you.